Hello, everybody. My name is Luis Silva. I'm a physician and researcher here at the University of Minnesota. If you received this video, it's because you demonstrated interest in the research we are pursuing with our research group, which is using artificial intelligence to streamline stroke research, to streamline research in neurology. What if I told you artificial intelligence could help science? And I'm not talking about using ChatGPT to write you a whole literature review with citations, although it can definitely do that. I'm talking about the field of natural language processing in general. Natural language processing is the specific field of artificial intelligence that deals with the problem of trying to make the computer understand text. It's a problem very hard to deal with. Multiple approaches have been tried, and one of the first cases, one of the first few success cases of natural language processing was text classification. More specifically, it was classifying email into regular email and spam. I don't know if you guys were around in the early 2000s using the internet, but a lot of what we saw on our email inbox was spam, and there was no spam filter, so your check inbox was just filled with spam. And a lot of researchers try to get a way for us to deal with that problem. One of the first few ways was using natural language processing, was using word counts. You would basically just count the words in an email and see how similar they are to other spam emails. It's a very, very simple, very archaic process in natural language processing, but it did a pretty good job creating those first spam filters. And in the early 2010s, we upgraded from word counting to representations of words as vectors in space. If you like linear algebra, I don't expect you to like linear algebra, by the way, but if you like linear algebra, you can kind of see where this is going, because if you decompose the vectors, if you kind of add and subtract vectors, you can have a pretty good understanding of what words can mean. For example, king plus women equals queen, because you're decomposing vectors and you're trying to find a point that's closer to the vectors you decomposed. And you can imagine that's very good for translation. In fact, Google Translate for the longest time used to use this approach to try to translate languages, because if you have a representation of words in space in two different languages, it's very easy for you to concatenate one word from one language to the other. This is just for you guys' pleasure and curiosity. When you look for a paper in artificial intelligence, and more specifically in natural language processing, you'll see the name of the researcher here on top, and you see their company on the bottom. We usually don't see their university, because most of the prime researchers for natural language processing specifically are in OpenAI or Google or Facebook. So you'll see their company on the bottom. And this is the first one to describe those vectors in space, which is called word-to-vec representation. What about King James? If I say King James, for a history buff, you might think of the guy who created, quote unquote, the King James version of the Bible. Or if you're a basketball nerd like me, you're gonna think about King James, LeBron James, one of the best basketball players to ever play the game. And the problem with word-to-vec is, if you give it two sentences like that, King James is better known for his contributions to the most sold version of the Bible, or King James once again scored 30 points in LA to guarantee a Lakers win over the Celtics. Word-to-vec can only see one word at a time. It doesn't understand the whole context of what's being said. So that's one of the greatest setbacks of word-to-vec. It really isn't understand. It isn't really capable of understanding phrases. And that's where recurrent neural networks come in. I'm not going to get too much into the details of what they mean, but basically what they can do is they can interpret it one word at a time using those hidden layers of the neural network to make a representation of the word. And in that sense, it can have an understanding of phrases as well, and not only of specific words. And that's how we got the first chatbots. The first chatbots were developed using recurrent neural networks, because they were able to understand phrases, and because they were able to generate phrases, because they have an understanding of how language is sequential. But the problem with this technique with recurrent neural networks is, the longer you are away from the word you're trying to interpret it, the harder it is, the less memory, quote unquote, the model has. So for example, if we look here at the model trying to understand the quotation mark here is represented by this dark orange, and the what, which is the word that it's in the beginning of the sentence, is represented by black. And this is a representation of how much memory the model has of the word what, it has very little representation of the word what, and it's skewed towards words that are closer to the end of the sentence. So that's a big problem with recurrent neural networks, and it's very hard for recurrent neural networks to understand large chunks of text. And we as humans, we speak in large chunks of text. Me right now, I'm doing a whole text and trying to explain something that's kind of complicated to you. And if I use recurrent neural networks to try to understand that, it's not going to be useful just because it's too long of a text. And the way around it was the attention architecture. Now, the attention architecture nowadays, it's been used for everything from ChatGPT, BERT, to DALL-E, to Midjourney. Everything uses attention, right? And so attention architecture, if you start to understand more about artificial intelligence and the very, very state-of-the-art technology in artificial intelligence, you start to see a lot of this image here. This is an image that I pulled from the BERT paper, the paper that first described attention architectures back in 2019. It's a great architecture. And what basically it allows us to do is it allows us to understand the relationship between the words, which is something that they call attention, right? So, for example, how related are the words origin as compared to the word speed, or how related are the word day as compared to the word traffic? And it can, in a text, in a whole big giant text, it can compare and contrast how different words are related to each other. And in that sense, it can get a very good understanding of what the text means and the contextual meaning of the text itself. If we look here, right in the middle, smack in the middle, we have BERT Large. Now, BERT Large is the largest model of the BERT. Google developed BERT's model. And it has 340 million parameters. Parameters are basically words and text. It uses in order for it to be trained as a model, in order for it to construct those attention architectures. And BERT can do a lot of things. We're probably going to use a lot of BERT. BERT is very good for specific tasks, but it's not as good as ChatGPT. And the only difference is because ChatGPT just uses billions of parameters, billions of words more than BERT uses, and that's why ChatGPT can have that quote unquote human-like characteristics when it's interacting with us, just because of the size and how many texts there are. And there's so many text that's in ChatGPT that it can understand context in multiple ways. It can understand how Donald Trump speaks. So if you ask ChatGPT to explain why it's better than BERT, it's going to give you a pretty good impersonation of Donald Trump. And that's just because it has a lot of text. If you ask it to do the same thing with Jerry Seinfeld or with any other famous person on the internet, it's going to be able to do that just because it was trained in a very, very large amount of data. Jokes aside, what about patients? What about research, right? That's what we're trying to do at the end of the day. Our research interest is the modified ranking scale. For those who know about stroke research, you'll know that the modified ranking scale is a scale that measures the functional activity of a person after a stroke mainly, but it can be used for anything. It's mainly used for stroke, and all the large trials in stroke use the modified ranking scale as their gold standard to compare treatments. These were all trials recently published in the last 10 years. All of them use the modified ranking scale as their primary outcome. And what about observational studies? Observational studies, the same way, they still use the MRS, but the MRS is assessed through medical records, right? Because in clinical trials, of course, you're there, assessing the patient yourself, but in observational studies, you're doing it through EPIC, through chart review. The thing is, electronic health records, they have a lot of information that is unstructured, that is disorganized, that you cannot put on a table. And in science, we of course need a lot of structured data for us to have an understanding of what's going on. And for example, in EPIC, we have a lot of text. Text is considered unstructured data, and we're trying to transform text into structured data, into a table that we can put up in Excel or any sort of program that can interpret tables. And what we do as researchers, a lot of what we do, especially for observational studies, is trying to transform unstructured data into structured data. More specifically, in the case of our research group, we try to make text into modified ranking scores. Trying to transform text into modified ranking score falls into the category that we're talking about. And we've been pretty successful at doing that. We have an up-and-coming manuscript that's going to be published very, very soon that is compared to treatments of stroke that were given here at the University of Minnesota. It wasn't a clinical trial or anything like that, but we definitely used that technique of using people to assess and to classify patients based on their records in order for us to achieve this scientific outcome. But we can use the models. We can use BERT, we can use ChatGPT, we can use BART, we can use anything that it's in the Hugging Face library to come up and take that text and transform it into a modified ranking scale. It's kind of the same idea of classifying email as spam. We're just going to classify a bunch of text into the modified ranking scale. It's a text classification problem, the same way classifying emails is a text classification problem. Okay, Luis, but what do you need of me, right? I'm not asking you, right? What do I need of you? Well, I need you to train the model. If you receive the invite, it's because you know a lot about patient care and you have an understanding of neurological functional outcome, and that's what I want you to do. I want you to train the model to understand that. So you're gonna read the text that it's in the EHR, and you're gonna assign an MRS. That's basically what you're gonna do, and that's gonna make the training necessary for the model to be then later be able to predict those modified ranking scores. So what do I need specifically? I just need 2 patients classified per day. That's it. You're gonna come home, after a day. You're gonna make a cup of tea, make a cup of coffee, depending on your cultural background. You're gonna log into Epic. You're gonna look at 2 charts, and you're gonna tell me your best guess of the modified ranking scale. That's it. If you do it 2 by day, we're gonna have a lot of text to be classified and a lot of information for the model to be trained on, and that's the goal for us for sure. And how's that gonna run? You're gonna be assigned a weekly list of records that you should assign those MRSs for. Those MRNs for. And through a chart abstraction in Epic, you find those patients and classify them. And eventually, you also input that classification into the REDCap database, and this data will be used to train the model. So what is there for me to gain, what is there for you to gain actually from this research? My bad. If you do classification of 150 patients, I guarantee your name is going to be on the author list. I guarantee it. And I hope this is going to be published, and I hope I'm going to work very hard for this to be a very impactful research, because I really believe on the capabilities of artificial intelligence to streamline observational research. I think it would be a better use of our time as researchers if we could do anything else but chart abstraction. So hopefully this is the last time anybody has to do chart abstraction for the modified ranking scale. So what if you like this? What if you're interested in participating? Shoot me an email, silva@umn.edu. You probably already have my email. So if you like it, just shoot me an email. We're going to start training. You're going to receive a video very similar to this one, and you're going to be trained on the MRS. I'm going to show you how to use the REDCap and stuff like that. But that's it. There's nothing more to do. I think it's a pretty simple project, and I think you're going to love it, because we're going to discuss, how the model is doing, and we're going to have a lot of discussions about the future of the project together. I really want this to be a team building experience and a teamwork experience, and your experience is extremely valuable to us. So what do you say? Are you going to take the blue pill and continue in oblivion and not believe that artificial intelligence can be used in science, or not even participate in that and just have it happen all around you? Or are you going to go deep in the rabbit hole with me, and you're going to take the red pill and be one of the few guys that can say, I did I was on a paper that's used machine learning, that used artificial intelligence to tackle a real world problem? You let me know. Just shoot me an email. It was very nice talking to you, and I hope to see you soon.